Hello and welcome to m253. My name is Lapuz and we are doing checkpoint 5.46. In this checkpoint they want us to make an appropriate change of variables for this particular integral. It's a double integral over the region R of 4 divided by x minus y quantity squared, where R is a trapezoid bounded by the lines x minus y is equal to 2, x minus y is equal to 4, and then x is equal to 0 and y is equal to 0. And then they want us to write out the integral that results in this transformation. Alright, the first thing we probably would like to do is to write out our, or draw out our x and y region. We'll call this capital R, which is what they have. And I have the line x, let's do this in another color. I have the line x minus y is equal to 2. X minus y is equal to 2. I'd probably be easier for me if I wrote this as y is equal to x minus 2. So that is going to be a line with slope 1, y-intercept at -2. So it'll hit the x-axis here at +2. The other one is similar. X minus y is equal to 4. So that's the same thing over here, except I start with -4, and then I end up at +4 in the x-axis. And then I have the x is equal to 0, that's the y-axis, and then the y is equal to 0, which is the x-axis. So I have my region R, which is going to be this trapezoid, as they described. Okay, we want a transformation, and I'm going to draw the UV plane on this side because our transformation is generally this t transformation that goes from uv to xy. So in other words, our independent variables are going to be uv, and then over here we're going to get an x and a y, and both of these are going to be functions of u and v. So in other words, we want x is equal to something and y is equal to something. Alright, let's try to find out what that should be. I'm going to go by the functions that they have, or the boundaries for the regions that they have, and notice that there's an x minus y for both of them. And I see it here, and it goes from 2 to 4. So it seems like it would be a good start to let one of the variables, like u, equal to x minus y. And by doing so, we're going to have the x minus y equals 2 and x minus y equal to 4. That would be like just u limits. So u can go from +2 to +4. All right. So now we need to figure out what x is going to equal to, or I'm sorry, v. So we need v. We have x is equal to 0. Maybe we can start off by saying, what if we let x equal to v? So if we let x equal to v, what is our y going to equal to? Well, if we have this equation over here, well, if x is equal to v, we can solve for y. So we basically want to know what the relationship is between this x and y and then u and v. So if x was equal to v, we can solve for y here and put in the actual values of v. So u is equal to x, which is equal to v, we said, minus y. So if we solve for y, we'll bring y to the other side, and then we will, y is on this side, this is going to be v minus u. And I think that is our transformation. So x is equal to v, y is equal to v minus u. Let's just rewrite that over here. and then we have our transformation as functions of x and y. So we could use this set of transformation. This describes your t inverse transformation that goes from xy to uv, but we want to go from uv to xy since our arrow is in fact going in this direction. All right, now as for the limits, I think it's pretty clear that our choice of u, by the way, u is equal to x minus y, is also present here, so that's going to make our integral a little bit nicer as well. But now back to this question about the limits. Our u, since this would be equal to u, looks like u just goes from 2 to 4, so we can already have u going from 2 to 4 as a set of limits. And now let's figure out where v is going to go. To try to figure out where v is going to go, we are going to take a note to say v x is equal to 0. That's like saying v is equal to 0, so that's one of the boundaries over here. And then we need the other boundary is y is equal to 0. So if y is equal to 0, let's take a look at this equation here and set y equal to 0, and then we have v minus u, and that's equivalent to saying, oh, that's just saying v is equal to u. So then that must be our upper limit. So these must be our limits for v. So v is going to go from 0 to u. So I probably want to write this backwards, at least the way I write my limits of integration. The constant limits go on the outer integral, and I usually put that in the bottom, and then I put this on top. So if I say 0 less than or equal to v less than or equal to u, and then u goes from 2 to 4, I can see how I might be able to draw this now. So if we pretend that v is like the y, the vertical variable, I would have y is equal to 0 and y is equal to u or x. So I would have this v is equal to u line as our diagonal line, like y equal x. And then I would be looking at this as a type 1 region where I integrate with respect to v first on the inside. So I would draw a line parallel to the v-axis, and I would enter through 0, and I would exit through this v is equal to u. And then now u goes from 2 to 4, so if this is 2 and this is 4, I have my actual region drawn out. So let's call this S for this region, and there we have it. All right, so now let's rewrite this integral. What do we have? We have the integral, the double integral over r of 4 over x minus y quantity squared dA. So this is your x and y limits. And now we're going to rewrite this as the integral over the new region S over, this is 4 over, now this is going to be a u squared. And then instead of a dA, we have a Jacobian, which we have to compute. And then now we get du dv in whatever the appropriate order is. And so the order still has to be determined, especially since I'm looking at this and saying, okay, one of the limits is not constant. So it looks like v is going to go first, so I probably want to switch the du dv. All right, Jacobian. Let's figure out the Jacobian. The Jacobian is going to be, remember the notation is the partial of xy over the partial of uv. uv is our independent variables, and I want to take a look at this set of equations and take those derivatives. I want the derivative of x with respect to u, derivative of x with respect to v, derivative of y with respect to u, and then the derivative of y with respect to v. And that is going to be the derivative of x with respect to u is 0. There's no u's in there. Derivative of x with respect to v is 1. The derivative of y with respect to u, this is a u, and that's -1. And then the derivative of y with respect to v is +1. And the determinant is going to be 0 minus -1. So that's just going to be 1. So that's just a nice Jacobian. And finally, we're going to be able to rewrite this with actual limits. So our integral then would be the 4 over u squared. Our Jacobian is 1. And then I think we decided that v has to go first because v has a non-constant limit. It goes from 0 to u, and in our du, our constant limits from 2 to 4. Okay, that's all they asked for. You can, if you want, go ahead and integrate this. This is a really simple integral. The original integral wasn't too bad, but the region looks like it's not a type 1 or type 2, so you'd have to do this a couple of times. This way, we just have one integral of type 1 region, and the integrand itself is not bad. All right, so we'll stop there, and I hope that helps. Good luck.